Hi everybody, in this video we're going to go deeper into the whole idea of recursion as a way of solving problems using code, and we're going to be solving a very famous puzzle known as the Towers of Hanoi. It's this example that was partly contrived, maybe it's real, who knows, where there's some monks and their goal really is to move a stack of discs from one tower to another tower, and that seems pretty easy, just lift the discs, move them to a spot. But there are some rules and constraints that kind of make it a little bit more complicated. And so what we're going to do in this video is start by looking at what exactly the problem is by looking at a very simple example and some more complex examples, trying to kind of get in our mind the idea of the steps that are needed to make this a solvable problem, and then looking at the code very quickly to see how all of the stuff we have in our brain translates into things that our computer can understand. And then I'll actually refer you back to an article that I wrote about this that goes into more detail around the mathematical time complexity and things like that. And so first, let's talk about the example here. So imagine you have a handful of disks. In this case, we have 4 disks. They're at a starting point. I call them pillars here, but you can also call them towers. And the goal really is you take all these disks that are currently available at the very starting tower and then have them be available at the destination tower. So you start from all the disks on, at the beginning, starting position, and then have them move to the very end. Now, what makes this a little bit more complicated is that there are certain things that we need to follow, certain rules of the game, if you will. The first one is you can only move one disk at a time. So you can't just grab 3 or 4 disks and just have them be, plopped to a location. At each move, you take a disk from the top of any of the stacks and place it on another tower. And that's something that we'll see as part of the examples when we're walking through. And number 3 is the part that always gets to most people when it comes to oh, here's what makes it really complicated, is that you can only place a smaller disk on top of a larger disk. So as part of you moving the disks around, the one constraint you must always maintain is that the disk that you're placing something on is larger than yourself. And the victory, the winning condition really is achieved when all the starting disks are arranged in the same starting order on the destination tower. And the destination tower can be anything, but I've been using tower 3, the third tower, as our destination. But you can probably see examples online where other people play this game by having other towers be the destination. So just be aware that that might be a detail that might be more unique to how I'm solving it right here. So let's start with the very basic case. We have a single disk. There's nothing else going on. We have a single disk. It's at our starting point. And based on the rules that we have right now, the solution really is we take this disk and plop it in our destination. There are no other disks to think about. There's no combination of arranging disks from one location to another. None of that is there. Single disk is the easiest one to kind of start with, and that really is our base case. Now, let's start with 2 disks. Here's where things start to, hopefully shape up and highlight the complexity a little bit more. So we have 2 disks with the smallest disk on top as per the constraints that we have. And so the first move I make is I take the smallest disk and I kind of just move it to an intermediary tower. The middle tower right now, in this case, is our intermediary tower. And then the next step is, okay, we have a completely exposed larger disk at the beginning, no other disks for us to worry about. So I'm going to take that disk, plop it at the very end, and as you can imagine, the next step will be to take the disk from our intermediary tower and move it to the destination as well, maintaining the order where the largest disk came first and the next smaller disk, or a smaller disk in general, came next. Now, the other case is that where we have 3 disks. Now here's where things get a little bit more complex, and we can see some of the details really coming into the forefront. So what we have here is we have 3 disks at the beginning. So the first step is we can only move 1 disk at a time, and it has to be the topmost disk. So I'm going to move the topmost disk, in this case, to our destination. And the second thing I'm going to do is take our middle disk and place it in in our intermediary tower, what we're calling it, at least that right now. And the last step is so now we have largest disk at the front, the second largest disk in the middle, and then the smallest at the very end. And we know that what we really need to have is a situation where the disks are often arranged the other way around, where the largest should be really at the first tower at the destination. And so the intermediate steps now will require a little bit of shuffling of the disk from one location to another. So notice that I combined 2 steps. I move the smallest disk into the intermediary region, and then when I do that, it leaves the third spot exposed, and now the largest tower is now moved to the destination. And so you can see that both those moves very quickly. And now what we have is just a more simpler problem of the 2-disk problem we saw earlier, where a smaller disk is at the top and a slightly larger disk is right in the middle. And so now, because we have 2 spots that we need to kind of use as our intermediate towers, I move the smallest disk back to the beginning, or what I'm calling the beginning. It's actually our new intermediate tower. And the second largest disk moves to destination, and then the smallest disk now follows. And now after, I feel like 6, 7 steps, we now have, or maybe it's like, I think it's about 7 or 9 steps, I forget. We now have all of our disks arranged at the appropriate position. And this example really highlighted a big detail here. And that is this algorithm overall that we can kind of generalize. The goal really is to get the largest bottommost disk to destination tower. That's really our big goal. And you might have a stack of however many towers, how many disks, and the bottommost disk will be the largest one, and that needs to go to the very end. And then that repeats itself where every next largest disk keeps getting moved to the end, where ultimately the end result is you're going to have a perfectly ordered stack of disks, starting with the largest at the bottom to the smallest at the top. And the way we do that is by moving all of our disks, except for the largest one, from a starting tower to a temporary tower. That's what we saw in the 3-disk case on number 2. And once we've done that, the next step is to move the largest disk to a destination tower. And then the last step is to move all the disks except the new largest one from our temporary tower to the destination tower. I know this sounds like a little bit odd, but just pause the video for a second, get a piece of pencil and paper out, and just kind of draw some of these things out, and you kind of see how all these disks and the words I'm using here will kind of map out. And now if we had to go one step deeper and go more formal, the algorithm really gets simplified into 3 steps. The first step is move the top n-1 disks from a starting tower to a temporary tower, which means that the end disk, which is the largest disk, is what's left behind. And that's what number 2 calls out, where the bottommost disk, the nth one, is moved from a starting tower to the destination tower. And then the last step is because we moved the n-1 disk to the temporary tower, we want to undo that now and move the remaining n-1 disk from the temporary tower to the destination tower. So we're just basically swapping, in this case, where intermediate tower is based on whether you're in the first step or in the 3rd step. And so that kind of highlights another detail. There's so many number of details here, is that each tower's role is fluid. And so I've been giving our towers really strict names like starting, temporary, and destination, but I've been trying my best to make sure not call it like the first tower, the second tower, third tower. And the reason is that these names are helpful for us to understand what's going on. But as part of moving the disks around, depending on what disk is currently being moved and what stage of the problem solving you're in, each tower will play an interim role as a temporary location, a destination location, or the starting location. So it won't always be the case where the first tower is the starting location, the middle tower is the intermediary, and the 3rd tower is the actual destination itself. Each of them will play one of those roles very, very handily. So be prepared for that as you see some of this work. And so here's an example where, the step that we kind of outlined earlier, where we now have the smallest disk in the beginning, the middle one in the second largest in the middle, and the largest one at the end. What is our starting tower in this case? And you can see in this case, the starting tower is not the red disk at number 1. It's actually the intermediate disk that's going to be moved to position number 3. So that really was our starting tower. And you can imagine the intermediate tower being the first one. So here's a more visual example of a step that we kind of glossed over when looking at the larger example. So now that we've kind of seen that and seen the algorithm at a very high level, now all that really remains is the code. And the code is not very long, as you can see. There's maybe 1, 2, 3, 4, maybe 5 lines really that are doing real work. If you actually take the comments out and the declaration out, you only have 3 lines of code that's really being kicked down here. And so notice that we have a function called Hanoi, and it takes 4 arguments. The first argument is a number of disks. The second argument and the second, third, and fourth arguments really are the tower positions. And because the tower positions are fluid, I don't want to say it's always going to be the starting into temporary or the destination, but for the very first run of it, we know that's what it's going to be. And so when I look at the very end, how I'm calling it, I'm calling the tower, I'm calling the Hanoi function, passing a number of disks, in which case it's 3, and then I'm giving 3 names as a way for helping us visualize what's going on, the starting, temporary, and destination, which we know again will completely shift as the puzzle keeps running. And notice what's going on in our very first step. In the first step, all I'm saying is call this function, take n-1 disks, and move them from the starting position, which initially is going to be A, and move it to the temporary location, which is going to be right here, and then to ultimately to the destination. And likewise, in the last step, the second time I'm calling this function, I'm basically recreating the verbally in code step number 3. We just move the remaining n-1 disk from the temporary tower to the destination tower. So in the first one, we're moving all of the disks from the starting point to temporary, and then this last one, we're moving all the temporary disks away from temporary back to the starting point. And the nth disk, of course, is the one that's going to be moved ultimately to the destination, which will be our largest item. And so if we were to copy this code, run it in your browser, for example, what you'll see will be exactly a more verbal version of the things that we've been talking about earlier, where disk 1 is moved from starting to destination, disk 2 moves from starting to temporary, disk 1 is now moved from destination back to temporary, and you can see this whole thing play out as part of the explanation that we have been talking about. Now, this is one of those equations that is not particularly efficient. It actually takes a lot of steps. The more towers that you currently throw in there, the more disks you throw in there, the more complicated it ultimately gets. And so one of the reasons is that it's a fully recursive function, and it happens to end only after every combination of disks have been moved from one location to another temporarily and then moved back. And the more disks you add, you can totally imagine the number of intermediate steps that are taken before the largest disk is moved from where it is right now to its destination position. And if I look at I linked to the article in the description of the video below. There I kind of walk through the whole mathematical process for what is the running time of this particular one, which is, I think, like 2 to the power of n. So then, it's 2 to the power of how many disks there are. So not the most efficient solution, at least not in the way that I have currently coded up here. And you can look into detail in my article on how I got to that point. So in the real problem, as actually, I don't believe it's actually done by, these sound like a historical fiction. This is more historical fiction than an actual problem I think the monks were trying to solve. It's actually a famous mathematician came up with this problem and probably used that as an example of how to make this work. And the original problem states the monks had to move 64 disks from one location, the starting point, to the destination, and just using the approach we talked about earlier, where it's 2 to the power of n, or in this case 64. The amount of time it'll take for the monks to fully complete this task, if we kind of think about it in terms of fixed amount of time and all that, it's around 585 billion years. So it's going to take a long time, and I think the Andromeda galaxy will collide with the Milky Way and cause all kinds of damage. I think the 4 or 8 billion year mark. So I wouldn't worry too much about this problem causing it, because according to the solution, the problem is when the monks have moved all the disks from the starting point to destination, the world is supposed to end. So the world will end well before that, from the mentioned where the other galaxies will be colliding with us just based on the current trajectory. So there you go. A little bit of history, a little bit of, I guess, morbid curiosity about how this world's going to end, and also a little bit of JavaScript and code and recursive knowledge at the same time. So if you have any questions about this or any other topic, post in the forums at forum.crib.com, and I'll be happy to help answer any of them. And if you like these videos, tell your friends and enemies all about them. Hit subscribe to be notified of new videos that I might be creating and putting on the channel for you all to view. Follow me at Krupa on Twitter, where I post updates on content I create, cool things I found, and so on. And lastly, if you like to read things in more physical form or in a Kindle form, buy my book. I have a variety of books that I write, and both in terms of web development topics that are relevant to this video, but also about other topics that I'm always interested in, like animations or drawing on the canvas or arrays, which is a topic that for whatever reason I'm really curious and interested in. And so check out these books out. And so with all of this, I will see you all next time.